we learned that one of the great debates of the 19th century had been about how light travels through a vacuum. Light from the stars, in fact, can effortlessly travel trillions upon trillions upon trillions of miles through the vacuum of outer space. Experiments also showed that light is a wave, but if light were a wave, then it would require something to be waving. Sound waves require air, water waves require water, but since there is nothing to wave in a vacuum, we have a paradox. How can light be a wave if there is nothing to wave? So physicists came up with an idea called the ether, which filled the vacuum and acted as the medium for light. But experiments showed that the ether does not exist. Physicists were surprised when they first stumbled upon the Kaluza-Klein theory, a bold idea connecting gravity and electromagnetism by adding an extra dimension to space. This theory gave the simplest explanation of light, that it was really a vibration of the fifth dimension. If light could travel through a vacuum, it was because the vacuum itself was vibrating, because the vacuum really existed in 4 dimensions of space and 1 of time. By adding the 5th dimension, the force of gravity and light could be unified in a simple way. The old Kaluza-Klein theory had technical problems for many years, but more advanced versions, like supergravity and superstring theory, have fixed these issues. Now, scientists worldwide are exploring the idea of higher dimensions, believing it might be the key to understanding the laws of nature. Why can't we see higher dimensions? We know that any object can be described by giving its height, width, and depth. By giving 3 numbers, we can locate any position in space. If we want to meet someone for lunch in Kathmandu, we say, "Meet me on the 2nd floor of the building at the corner of Banchua Street and 1st Avenue." 2 numbers provide us the street corner, and the 3rd, the height off the ground. Even babies understand this. Tests with infants have shown that they will crawl to the edge of a cliff, peer over the edge, and crawl back. Babies also naturally understand directions like left, right, forward, backward, up, and down. So, the concept of 3 dimensions is something our brains understand from early age. Einstein further extended this concept to include time as the 4th dimension. Let's take that previous example. To meet that someone for lunch, we must specify that we should meet at, say, 1:30 p.m. in Kathmandu. That is, to specify an event, we also need to describe its 4th dimension, the time at which the event takes place. Scientists today are interested in going beyond Einstein's conception of the 4th dimension and the current scientific interest on the 5th dimension and beyond. How do we see the 4th dimension? The problem is we can't. Higher dimensional spaces are impossible to visualize. It's like trying to explain, no matter how nicely we describe red color to a blind person. That's not impart any meaning to him. Our brains evolved to handle stuff in 3 dimensions quickly, but they don't need to deal with more dimensions for survival. So imagining things in 4 dimensions is a challenge because it did not help someone fend off a charging tiger. Lions and tigers do not lunge at us through the 4th dimension. Physicist Peter Freund says that laws of nature become simpler and better when expressed in higher dimensions. It's like a cheetah in a zoo. It looks sad and broken, but in the wild it's powerful and graceful. For decades, physicists have wondered why the 4 forces of nature appear to be so fragmented, why the cheetah looks so pitiful and broken in his cage. The fundamental reason why these 4 forces seem so dissimilar is that we have been observing the caged cheetah. Our 3-dimensional laboratories are sterile zoo cages for the laws of physics. One model which helps us conceive of it easier and understand it better is a tesseract or hypercube. This is a cube within a cube. Imagine you have a cube. Each face of the cube is a square. Now picture another cube connected to the first one, not beside it, but in a direction perpendicular to our 3-dimensional space. This creates a tesseract, a 4-dimensional shape. In a tesseract, you would have inner cubes that are connected through a 4th spatial dimension. We can't directly see or experience this in our 3-dimension, but we can use math and geometry to represent and understand it. Einstein faced many challenges and failures in his early life. His teachers thought he was a dreamer and even suggested he drop out of school. He struggled to find a job, earned very little money tutoring students, and faced rejection for teaching positions. Eventually, he found a low-paying job as a clerk at the Swiss patent office. Despite these setbacks, Einstein's genius lay in his ability to ask simple yet profound questions. As a child, he wondered what light beam would look like if you could catch up with it. This question led him to develop the principle of special relativity, stating that the speed of light is constant in all moving frames. To understand this principle, imagine trying to catch up with a light beam in a speeding car. According to relativity, no matter how fast you drive, the light beam always appears to move at its constant speed. This seemingly impossible scenario led Einstein to the conclusion that time slows down for objects in motion, and space itself undergoes distortions. In everyday life, these relativistic effects are too small to notice due to the high speed of light. However, Einstein's groundbreaking ideas have profound implications for understanding space, time, and the nature of the universe. Einstein's theory of special relativity suggests that time is the fourth dimension, linking space and time in a new way. This idea revolutionized our understanding of the universe. Unlike the old belief that time beats uniformly everywhere, relativity shows that time can vary depending on how fast something is moving. Imagine space and time as interconnected dimensions that can rotate into each other. This rotation is described by special relativity, simplifying the laws of nature. For example, Maxwell's complex field equations in electromagnetism become one elegant equation when time is treated as the fourth dimension. This simplification reveals a higher symmetry, demonstrating the beauty of physics. The concept of the fourth dimension also explains the relative aging of objects in motion. In a hypothetical scenario, a person traveling in a fast rocket might age only a few moments while years pass for those on Earth. This idea challenges the assumption that time ticks uniformly everywhere. In essence, Einstein's theory highlights how adding higher dimensions, like time as the fourth dimension, helps unify and simplify our understanding of the laws of nature. Einstein had a groundbreaking idea that changed how we understand the universe. He thought, if space and time could be combined into one thing called spacetime, then maybe matter and energy could also be connected. This meant that everything we measure, like rulers and clocks, might change. He found that as objects, like a speeding car, get closer to the speed of light, they shrink and clocks slow down. He also discovered that the mass of an object increases as it speeds up, and this extra mass comes from energy. This was a big deal because it challenged the idea that mass and energy are separately conserved. Einstein's famous equation, E equals mc squared, shows that a small amount of matter can release a huge amount of energy. This revealed that matter is like a storehouse of energy, and a tiny bit of it can unleash a lot of power. By connecting the fourth dimension with space, Einstein united matter and energy, creating a concept called matter-energy. This idea had a huge impact, leading to the development of powerful things like the hydrogen bomb. Einstein didn't stop there. He wanted to understand gravity. He used a simple idea called the equivalence principle, which said that the laws of nature in an accelerating frame are the same as in a gravitational field. This helped him solve problems like whether gravity affects light. His discovery showed that if light bends under gravity, it means space itself is curved. Einstein predicted that the presence of the sun would bend the path of light from distant stars, a phenomenon confirmed during solar eclipses. This idea is encapsulated in Mach's principle, which states that the bending of space is directly related to the amount of energy and matter within that space. Consider our universe. It is a large hypersphere, which is like a sphere in 4 dimensions. In this curved space, peculiar things happen. For example, if you look ahead, light can circle completely around the hypersphere, creating the illusion of seeing someone with their back facing you, who looks just like you. This strange scenario is because you are the only person in this curved space. Now, picture living on a hyperdonut, which are even more bizarre universes with unique properties. For instance, on a hyperdonut, you could see an infinite sequence of yourself holding hands in every direction due to the way light travels around the donut. These examples illustrate how living in a universe with curved space and time can lead to fascinating and unexpected situations. In 1953, a young physicist named Peter Freund encountered the concept of the fifth dimension during a talk in Romania. The idea was based on Kaluza-Klein theory, which used 5 dimensions to potentially unify the theories of light and gravity. Now think of flatlanders living on a plane. Likewise, a scientist on Flatland may make the outrageous claim that traveling through the third dimension is possible. In principle, a flatlander could rise off the surface of Flatland. As this flatlander slowly floated upward in the third dimension, his eyes would see an incredible sequence of different parallel universes, each coexisting with his universe. Because his eyes would be able to see only parallel to the surface of Flatland, he would see different Flatland universes appearing before him. If the Flatlander drifted too far above the plane, eventually he would return to his original Flatland universe. This concept agreed with experiments due to the smallness of the fifth dimension. It also posed a challenge. The tiny size meant experiments couldn't confirm the theory's correctness, leading to skepticism and the notion that it might not even be testable. The tidal wave unleashed by this theory of the subatomic world completely swamped research in Kaluza-Klein theory. The new theory was called quantum mechanics, and it sounded the death knell for Kaluza-Klein theory for the next 60 years. Worse, quantum mechanics challenged the smooth geometric interpretation of forces, replacing it with discrete packets of energy. Quantum mechanics overshadowed Einstein's work for decades, particularly his geometric theory of the universe. The quantum revolution made Einstein seem outdated, with younger physicists focusing on quantum theory rather than the theory of relativity. This theory challenged common sense, reducing everything to probabilities and unveiling unsettling philosophical implications. Experimental verification, such as the famous double-slit experiment, confirmed its peculiar predictions, like particles behaving as both waves or particles simultaneously. The 4 key principles of quantum mechanics include the idea that forces result from the exchange of quanta. Different forces involve different quanta. The Heisenberg uncertainty principle preventing precise knowledge of particle properties, and the possibility of particles tunneling through barriers. Quantum tunneling exemplified by the tunnel diodes. Quantum tunneling, exemplified by the tunnel diode, has practical applications in electronics, making devices like television sets and computers. In 1971, Gerard Hof changed the game. Earlier theories, including one by Yang and Mills in 1954, suggested the weak and strong forces were caused by particles. But these theories had issues. Hof showed a way to make sense of these theories, and suddenly everything fell into place. The key was the Yang-Mills field, revealing the nature of particle interactions. Before this, physicists faced problems in their calculations due to infinite values in quantum corrections. The Yang-Mills field seemed too complex for practical use. But Hooft, inspired by his advisor Veltman, showed that when symmetry is broken, the Yang-Mills field gains mass but remains finite. He resolved the infinities, proving the Yang-Mills field is a valid theory. This discovery was a turning point, confirming the theory proposed by Weinberg and Salem for weak interactions. The Yang-Mills field's application to strong interactions and its role in nuclear matter solidified its significance. Edward Witten, a leading theoretical physicist, is known for his groundbreaking ideas that influence the physics community. His brilliance is often compared to Einstein. Witten's most ambitious project is superstring theory, aiming to unite Einstein's gravity theory with quantum theory. He is determined to refine this theory and explore its origins, potentially revealing insights into the moment of creation. Superstring theory involves strings vibrating in 10 or 26 dimensions, presenting an unusual geometry. The essence of string theory lies in explaining both matter and spacetime. It addresses questions about particles, clarifying why there are so many types. In this theory, particles are tiny strings vibrating at different frequencies, and each vibration corresponds to a distinct particle. This explains the variety of particles in nature. Moreover, string theory extends beyond particles to explain spacetime itself. As strings move, they undergo complex motions, breaking into smaller strings or combining with others. The theory imposes stringent conditions on spacetime, leading to the surprising discovery that Einstein's equations can be derived from string theory without assuming them. This comprehensive theory links matter, energy, and spacetime, providing unified understanding of fundamental laws. String theory, a complex idea in physics, has a mystery. It works best in 10 or 26 dimensions, and scientists wonder why. If it had only 3 dimensions, it wouldn't unify physics laws well. The theory's essence lies in higher dimensions. When analyzing how strings behave in n-dimensional space, unwanted terms arise, harming the theory. But these terms are tied to pushing physicists to set n to 10. Turn string theory uniquely demands this fixed dimension. But why 10 dimensions? The answer involves mysterious math called modular functions. Srinivasa Ramanujan, a brilliant mathematician from India, discovered these functions. His work, full of magic numbers, coincidentally aligns with string theory. The number 24, prominent in Ramanujan's functions, leads to 26 dimensions in string theory. Ramanujan's functions generalization replaces 24 with 8, resulting in the critical number 10 for superstrings. It's like a deep numerology, and scientists can't clarify why 10 dimensions are crucial. Ramanujan, born in 1887, showed extraordinary mathematical skills early. A chance encounter with a math book marked his only exposure to Western mathematics. His genius led him to rederive European math, and his work reached Hardy, a respected British mathematician. Their collaboration in Cambridge showcased Ramanujan's incredible theorems. David Hume, an 18th century philosopher, argued that experimental verification is crucial for theories, but he faced a challenge when it came to theories about creation. Hume believed experiments needed to be reproducible, but since creation is a unique event, it cannot be replicated, making it impossible to verify such theories. In a similar way today, the theory proposing 10 dimensions faces a challenge in experimental verification due to the extreme energy levels required. One indirect approach was the superconducting supercollider, a colossal machine intended to collide protons at high energies. Unfortunately, political opposition led to the cancellation of the superconducting supercollider, leaving the scientific community without a means to directly test the theory. Since the superconducting supercollider won't be built, and it can't detect low-energy superstring particles, scientists are exploring other options. One idea is to study cosmic rays, which are high-energy particles from space. Unlike controlled rays in lamps, cosmic rays have unpredictable energies, making it challenging to conduct precise experiments. Cosmic rays were discovered 80 years ago, and early studies were done with balloons and mountains. The most energetic cosmic rays detected so far have an energy level far beyond what the superconducting supercollider could produce. Even though this energy is much smaller than needed to explore the 10th dimension, scientists hope that deep within black holes in our galaxy, energies close to the Planck energy may be found. Orbiting spacecraft could help investigate these energy sources. History shows that when faced with untestable ideas, unexpected breakthroughs can lead to indirect experiments. In the 19th century, scientists thought studying star compositions was impossible until Fraunhofer used a prism and spectroscope. Similarly, unforeseen methods might emerge to explore the 10th dimension, perhaps using signals from the Planck energy. Looking at the history of science, there might be reasons for hope. Scientists like Witten believe that, in time, we'll be able to explore energies at the Planck scale. He compares it to the past when understanding why water boils at 100 degrees seemed impossible. Similarly, he suggests that even though testing 10-dimensional theory is challenging now, some scientists argue that not everything needs experimental proof. Eddington and Dirac, for example, emphasize the importance of elegant equations and theories over fitting experiments. Despite this optimism, the experimental outlook for the 10-dimensional theory appears grim. Testing it involves recreating a part of the Big Bang, a daunting task. In simple terms, we're exploring a question first asked in 1990. Where did the fifth dimension go? This relates to quantum theory and a phenomenon called tunneling, where even unlikely events have a small chance of happening. For instance, atoms can break apart through tunneling, which also explains radioactive decay. In the past, the universe, possibly 10-dimensional, started in a symmetrical state, but became unstable, tunneling into a 4 in the 6-dimensional universe. This transition is like a bedsheet curling up due to elastic bands snapping off, a process called symmetry breaking. The 10-dimensional universe had various ways to curl up, and the choice depends on solving complex quantum theories. Symmetry breaking is a common theme, seen in life stages, societal changes, and even explosive events like atomic bombs. When symmetry breaks, a new state with less symmetry is reached, like a princess falling off a smooth sphere. Regarding superstring theory, it's assumed that the original 10-dimensional universe underwent tunneling, leading to today's broken 4 and 6-dimensional universe. However, if our universe isn't the true vacuum state, and the true vacuum lies among millions of possibilities, it could lead to disastrous consequences, possibly creating bubbles with different laws of physics that rapidly expand, swallowing everything in their path at the speed of light. The journey from an ice cube to superstrings is described, emphasizing phase transitions as things heat up, leading to the formation of different states of matter. Finally, at extremely high temperatures, superstrings may emerge, and the very fabric of space-time could distort, potentially forming wormholes. To understand black holes and how difficult they are to find, we must first understand what makes the stars shine, how they grow, and how they eventually die. Stars are fascinating, and understanding their life cycle helps us appreciate black holes. Stars begin when massive clouds of hydrogen gas collapse under gravity, forming a nuclear furnace. This furnace burns hydrogen, creating helium and releasing energy that makes stars shine. As a star ages, it balances gravity, trying to crush it, and nuclear forces trying to explode it. Our sun, a yellow star, would eventually become a red giant, burning waste helium, and then a white dwarf. For more massive stars, the story is different. When they run out of helium, gravity takes over, leading to a supernova explosion, ejecting stellar debris that forms new stars. After a supernova, a neutron star, a dense remnant they remain. Heavy elements like those in our bodies are created in supernovae. When a star is much larger than our sun, gravity continues, squeezing it even after it becomes a neutron star. Without fusion to counteract gravity, the star collapses into a black hole. A black hole is so dense that light can't escape, making it appear black. All celestial bodies have an escape velocity, the speed needed to break free from gravity. A supermassive star might have an escape velocity equal to light speed, leading to a black hole. There are two ways to explain why black holes are black. One is that the force between the star and light bends its path into a circle, making it seem black. Another, based on Einstein's theory, involves space bending in a circle forming a hypersphere. The black hole's immense gravity disconnects this piece of space-time from its surroundings, creating a ripped space. The concept of an Einstein-Rosen bridge connecting two universes was initially thought impossible to traverse. Later, Roy Kerr's work introduced rotating black holes, suggesting the possibility of travel through a wormhole, a gateway to another universe. As a spaceship enters this bridge, it encounters unusual optical effects, creating illusions due to light orbiting the black hole multiple times. Can black holes be used for space travel like in Star Trek? When we travel through space, like in Star Trek's Warp, Baxter 5, it involves bending space and time. In the show, dilithium crystals power the Enterprise, creating a warp in the space-time continuum. It's like pulling a table towards you on a slick floor. You haven't physically moved, the space has contracted, and you've moved through a wormhole. If we insert our hands into the window from two different directions, then it appears as though our hands have disappeared. We have a body but no hands. In the alternative universe, two hands have emerged from either side of the window, but they are not attached to a body. This shows some strange distortions of space and time in multiple connected spaces. But Creating wormholes or dimensional gateways requires a vast amount of matter energy, and quantum effects may close the opening, making travel impossible. Whether wormholes are physically relevant or just a crazy idea awaits answers from a 10-dimensional theory, which combines quantum theory and relativity. Wormholes might also allow time travel, but this remains a fascinating and speculative consequence of multiple connected universes. Can we go back in time like in Herbert George Wells' The Time Machine or Back to the Future? The idea of time travel raises exciting possibilities like fixing past mistakes or altering historical events. However, it poses challenges. In special relativity, time travel is seemingly impossible, as exceeding the speed of light would make mass impossibility. Einstein recognized this impossibility, as humorously captured in a limerick. General relativity, a more powerful theory, allows for certain forms of time travel, but the energies required are enormous, breaking down Einstein's equations. Quantum theory takes over in regions where time travel could occur, raising complex questions. Hyperspace theory, uniting quantum space, might provide answers. Time travel, if widespread, would disrupt causality and history. Imagine millions meddling in the past, rewriting events, or even causing chaos. The battlefields of history could be altered, and key events might never be resolved. This challenges the very idea of history, making it constantly changing and impossible to understand. Many scientists find this prospect unsettling. Cosmologist Stephen Hawking even suggests that the absence of time-traveling tourists from the future could be evidence against its possibility. Time travel has two main paradoxes. The first is meeting your parents before you're born, like in Back to the Future. If you accidentally change their meeting and your birth doesn't happen, you disappear. The second paradox involves events with no clear beginning, like a person getting help from their future selves to invent a time machine. A crazy example of the second paradox is in a story where a person becomes their own mother, father, son, and daughter due to time travel. It creates a twisted family tree where they are essentially their own ancestors and descendants. In Einstein's theory of relativity, there's a concept called world lines. It's like a path in space-time that represents your entire history. Even after you die, the world lines of the molecules in your body continue. You can't cut or change world lines, according to Einstein. If you go back in time and meet your mother before you're born, you can't make changes that would erase your existence, as your world line cannot be cut. However, fulfilling the past is possible, creating closed loops in time. The debate among scientists is whether these closed loops, called closed time-like curves, are allowed by both general relativity and quantum theory. Einstein's friend, Kurt Gödel, a mathematician, discovered a solution to Einstein's equations in 1949 that allowed for certain types of time travel. This was the first time that time travel had a mathematical basis. Using Einstein's equations, Gödel showed that a universe with slow rotating gas or dust could permit time travel. He found paths where a particle could come back and meet itself in the past. This challenged the idea that time always moves forward like an arrow. However, Gödel's assumption about the rotation of the universe was experimentally ruled out, making his solution unlikely for our universe. Despite this, it raised the possibility that if our universe did rotate, time travel might be possible. In 1963, a new solution by Newman, Anti, and Tamburino allowed for closed time-like curves in time travel without the need for a rotating universe. This discovery and others challenged the experimental dismissal of time travel solutions. To overcome skepticism, they addressed common objections to using wormholes as time machines. Obstacles included the intense gravitational forces in black holes, potential instability, the need to surpass the speed of light, quantum effects, and time distortion wormholes. Thorne, usually skeptical about time machines, became interested when Carl Sagan asked for a scientifically accurate way to break the light barrier in his novel Contact. Thorne and his colleagues worked backward, defining the characteristics they wanted in a time-traveling wormhole, and then calculating the energy needed. They surprisingly discovered a simple solution, calling it the transversible wormhole. This wormhole was distinct from typical black hole solutions, making it more feasible for time travel, but creating Such a wormhole requires an exotic form of matter at its center, which might challenge our current understanding. Thorne's time machine plans might disappoint those expecting something like Herbert George Wells' time travel chair. Instead, it involves advanced concepts. One version uses two chambers with parallel metal plates and intense electric fields, creating a wormhole. The chambers experience time differently, enabling time travel for someone entering a wormhole. Another design involves a cylinder of exotic matter that warps space and time, creating a wormhole for time travel. Thorne's mathematical reasoning is solid, showing that Einstein's equations allow for time differences in wormholes. The challenge is generating enough energy in exotic matter. Quantum theory, demonstrated by the Casimir effect, shows that negative energy is possible between parallel plates. Placing such plates at wormhole entrances may create negative energy. But debates persist. Stephen Hawking raises concerns about radiation at the wormhole entrance, closing it. Superstring theory, a quantum mechanical theory, including general relativity, could determine if the averaged weak energy condition is achievable, and if wormhole entrances stay open for time travel. Stephen Hawking, a renowned cosmologist, faced immense challenges due to an incurable disease, but continued groundbreaking research. Despite losing control of his body, he tackled big scientific problems, even exploring the unification of gravity and quantum theory. Hawking, the Lucasian professor of physics at Cambridge University, initiated quantum cosmology, merging quantum theory and cosmology. His idea involves treating the entire universe as a quantum particle, leading to the concept of an infinite set of parallel universes. In this quantum cosmology, the wave function of the universe spreads across all possible universes, with our universe having a higher probability. Hawking suggests that these universes can collide through wormholes connecting different universes. Scientists are having a debate about something called the anthropic principle. It's about whether the universe and its physical constants were precisely set up to allow life, like us, to exist. There are two versions: the weak version, which says the existence of intelligent life helps us understand the constants of the universe, and the strong version, which suggests all constants were precisely chosen to allow life. The weak version makes sense, and certain conditions are needed for life to exist, like the right chemical and physical constants. However, the strong version, which implies a deliberate choice by a higher being, is more controversial. This debate was dormant for a while, but got revived by Stephen Hawking's ideas about an infinite number of parallel universes. Some believe that if there are many universes with different constants, it might explain why life is possible in our universe. The second controversy is called Schrödinger's cat problem. It's a bizarre situation in quantum theory where something can be in two states at once until observed. Some physicists deal with this by suggesting a universal consciousness, while others simply wish the problem away. The many worlds theory, which suggests multiple universes where all possibilities happen, is also making a comeback. In 1957, a physicist named Hugh Everett suggested that the universe constantly splits into different paths, creating an infinite number of universes. Each universe is connected to others through these splits. This idea, known as the many worlds theory, proposes that all possible quantum worlds exist simultaneously. For example, if we consider Schrödinger's cat, in one universe the cat might be alive, and in another it might be dead. This theory tries to resolve the paradoxes of quantum theory. However, many physicists haven't favored the many worlds theory due to its complexity and lack of simplicity, which physicists generally prefer. Occam's razor, a principle in physics, suggests choosing the simplest explanation. Since communication between these many worlds is not possible and can't be tested, some physicists find it reasonable to eliminate them. There are two big ideas in physics: Everett's many worlds theory and Hawking's wave function of the universe. The difference is that Hawking's theory involves tiny wormholes connecting parallel universes. These wormholes are super small, like 100 billion times smaller than a proton, making human travel impossible. Even if these connections exist, major jumps between universes are rare and might take longer than the lifetime of the universe. Imagine a scenario where you enter a universe exactly like ours, but with one small difference. This idea isn't new. It's been explored in stories like Random Quest. The protagonist, Colin Trafford, switches universes and faces a world with different history and even becomes someone else entirely. Now let's talk about Sidney Coleman, a physicist who's into wormholes. He claims these wormholes might help explain a big mystery in physics, the cosmological constant problem. This problem involves the weird relationship between vacuum energy and the expansion of the universe. Coleman suggests that wormholes could cancel out this unwanted energy and keep the universe stable. If he's right, it could mean that wormholes are vital for the stability of our universe. However, we're still in the early stages of understanding this, and it might take a better understanding of quantum gravity to solve these mysteries. The Planck length, where these events happen, is a challenging frontier in physics. The hope is that mastering the energy at this level could unlock incredible possibilities, but we're not there yet. Physicist Paul Davies once commented on what to expect once we have solved the mysteries of the unification of all forces into a single superforce. He wrote that we could change the structure of space and time, tie our own knots in nothingness, and build matter to order. Controlling the superforce would enable us to construct and transmute particles at will, thus generating exotic forms of matter. We might even be able to manipulate the dimensionality of space itself, creating bizarre artificial worlds with unimaginable properties. Truly, we should be lords of the universe. But achieving this level of control requires a massive amount of energy, much more than our current technology can provide. It might take many centuries before we develop the necessary technology to harness this power. The comparison is made with the exponential growth of technology throughout history, showing that our understanding and use of energy have rapidly increased over time. It starts with humans relying on their own muscle power, gradually increasing with the invention of tools and the shift to agriculture. The Industrial Revolution marked a significant leap, allowing humans to command much more energy through steam-powered engines. Subsequent discoveries, such as the mastery of electromagnetic and nuclear forces, further multiplied the available energy. Futurology, or the prediction of the future from reasonable scientific judgments, is a risky science. It's about the challenges in making accurate predictions due to linear thinking and the exponential growth of knowledge. Past predictions, like those about blimps for transatlantic travel, often turned out to be wrong. The civilizations are categorized based on their energy control. Type 0, like our current state. Type 1, controlling a whole planet. Type 2, controlling the power of the sun. And Type 3, controlling the power of an entire galaxy. The transition from Type 1 to Type 2 is estimated to take about 1,000 years, allowing for space colonization and mastery of gravitational forces. The leap to a Type 3 civilization, controlling the power of a galaxy, might take several thousand years. At this advanced stage, manipulating much larger energies becomes possible, potentially leading to mastery of the 10th dimension. Physicist Freeman Dyson thinks about big questions like space exploration, aliens, and the future of our civilization. Unlike many other scientists, Dyson's mind jumps around a lot. He believes our space program should change direction and focus on creating a small and smart space probe called Astrochican. This Astrochican would be a mix of machine and animal, using advanced biology and technology to explore space more efficiently. Dyson believes we can become a Type 1 civilization in a few centuries. He thinks it's not too hard to move from one type of civilization to another. He predicts that with a steady 1% growth per year, a civilization can reach Type 3 status within a few million years. Dyson also says that a civilization with a strong desire to expand will eventually cover a whole star or even a galaxy. But he sees a challenge in going from a Type 2 to a Type 3 civilization because of the speed of light. Dyson wonders if it's possible to break the speed limit and explore hyperspace. But he's not sure, as the energy needed for such exploration might be too much. He suggests that reaching the smallest possible distance, the Planck length, could be a tough natural barrier for all civilizations. Maybe one day we will meet aliens from a civilization more advanced than ours, and they might share their cool technology with us. But the problem is, we haven't found any signs of advanced civilizations in our solar system or nearby space. Our space probes found that Venus and Mars, the two planets we thought might have life, are pretty harsh and barren. Scientists also tried to listen for signals from intelligent beings in space, using something called SETI, but they haven't found anything yet. There are lots of stars in our galaxy, and according to some estimates, there should be many planets with intelligent life. But we still haven't seen any signs of them. Scientists think about what will happen to the atoms in our bodies after we die. Most likely, our molecules will end up going back to the sun. The sun is about 5 billion years old, and will remain a yellow star for another 5 billion years. But when it runs out of hydrogen fuel, it will become a red giant, expanding so much that it will reach the orbit of Mars. The Earth will be fried by the sun's extreme heat, and our body's molecules, along with the Earth, will be consumed by the sun's atmosphere. Billions of years from now, Earth will experience extreme changes, with melting ice caps and boiling oceans. Eventually, the entire planet will face a catastrophic end as the atmosphere evaporates into space. Though our sun's demise is inevitable, it gives us plenty of warning compared to sudden events like supernovas. After this happens, humans, if we survive that long, will likely have left the solar system. Looking even further into the future, the Milky Way galaxy where we live will also die in a few billion years. Our galaxy is on the Orion's spiral arm, and it will collide with the Andromeda galaxy about 5 to 10 billion years. This collision will destroy our galaxy, but the stars within it are so spread out that direct collisions will be rare. But the universe itself faces a more significant threat over the course of billions of years. The death of the universe might happen when all stars run out of fuel. If the universe is open, it will expand forever until temperatures reach near absolute zero. If it's closed, there could be a fiery big crunch. Even for an advanced civilization, this is a serious threat. The question remains, can mastering hyperspace save us from the universe's ultimate end? The fate of a civilization's ability to harness hyperspace power depends on its technological development and the ability to navigate potential disasters. In the early years after the nuclear age, there's a risk of self-annihilation due to technological advancement, outpacing social and political maturity. By the time a civilization reaches Type 3 status, it should have advanced social structures and technology to avoid ecological or natural disasters. However, even advanced civilizations face the ultimate catastrophe, the death of the universe. This inevitability has been understood since the 19th century. Presently, there's uncertainty about the fate because of the challenge in measuring the total mass of the universe accurately. The presence of dark matter, undetectable and not luminous, contributes to this uncertainty. The universe's demise can occur in a cosmic whimper, with perpetual expansion, or a big crunch where it contracts into fiery collapse. The fate depends on the total matter energy in the universe, determined by Einstein's equations. If the average density is below a critical value, the universe would expand indefinitely, resulting in an entropy death, where the universe approaches absolute zero temperature, causing a gradual increase in chaos or randomness. The laws of thermodynamics play a crucial role in understanding this process. The second law, stating that entropy always increases, leads to a future where stars exhaust their fuel and the universe darkens. Eventually, protons and neutrons decay, and matter dissolves into smaller particles. In the distant future, as the universe nears absolute zero temperature, black holes become potential energy sources. Intelligent life might gather around evaporating black holes for survival. However, beyond a certain point, even black holes may exhaust their energy. Theories propose that, after an incredibly long time, quantum events might occur, potentially leading to a tunneling into another universe. While these events have extremely low probabilities, the infinite quantum future remains uncertain, leaving room for unexpected outcomes in the vast timescale of 10 to the power of 100 years. The The fate of the universe can be either a cosmic whimper or a fiery end, depending on its average density. If the density is too low, the universe will expand indefinitely, leading to a gradual cooling and entropy death. However, if the density is high enough, the universe will contract, culminating in a fiery collapse. During this contraction, distant galaxies will come together, and stars will rapidly approach each other. The rising temperatures would eventually vaporize all matter, causing planets to disintegrate. As temperatures continue to rise, protons and neutrons will be torn apart, leading to a scenario similar to a black hole devouring everything. Ordinary matter and intelligent life seem unable to survive this violent disruption, except for one potential escape route: hyperspace. Hyperspace travel might offer a way out of the Big Crunch by leaving space and time. Calculations based on advanced theories suggest a connection between 4-dimensional and 6-dimensional universes, potentially allowing intelligent life to exploit this link for escape. The scenario is reminiscent of science fiction stories like Isaac Asimov's The Last Question, where advanced computers tackle the mysteries of the universe. In these tales, even as stars die and galaxies fade away, the quest for understanding and potential solutions continues.